Yes, well, I posted a couple of things. An induction proof for Goldbach's conjecture. I think it works. I've read in Wikipedia how you can have bad induction proofs where there's some fault in the first premise, the k equals 1 case. But I don't think it applies here. I think the whole trick amounts to the graphic, call it, where you list 0 through n and then n counting up to 2n. Encapsulates all the numbers. So if the composite count is wrong for one case, it's wrong for all those numbers and all those cases. And if it's right, it's right. It's a little annoying because it's a pure logic proof that if you get into trouble assuming that it's false, Goldbach's conjecture, then the implication is that all primes map to composites. All primes on the lower 0 through n row map to composites on the n through 2n row. That seems a stretch, but Goldbach's conjecture is that there always exists at least one prime that maps to a prime in this context. So when you negate that, for one case, then the structure, the replication of n and the lower row 0 to n and n in the top row n to 2n, that's outside the hypothesis. And the stuff at the end there, the 0, 1 case, are not of the domain of interest, namely 2 through n. So everything in between is of the previous case, of the k case, and so k plus 1 also doesn't map correctly. It doesn't count composites correctly. That said, the number of composites is too many. It seems I've never seen a induction proof that had such a claim. Usually it's an algebraic form, like you're adding 1 plus 2 plus 3 or something like that, and you want to go through n, and you have a formula. I think it's something like k times k plus 1 over 2 or something like that. And the k case implies the k plus 1 case where you just algebraically add the new term, do some manipulations, and out drops your formula. It doesn't seem to be of that type of induction for sure. But nonetheless, is there a problem where your thing you're saying is a negation? The number of composites is too many. Is that an innovation? Is that a mistake? I think it's an innovation. I feel that the induction does take place, and the consequence is that there's always going to be a p in the lower row that maps to p above, and the sum is going to be 2n for any n. The other one that uses cross-classification. Just for a little break here, we'll go look at these, published on Vixra. The other one is uses cross-classification, and this one I'm more leery of than the other one, the hypothesis or induction one. This one, it, what you'd really like is a tighter calculation that the remaining cases that haven't been wiped out exist. That's what this one's about. You have some hope that you could tighten this up. How do you know the primes on the bottom row will line up with those at the top? Using one will demonstrate the logic. Consider the primes less than 44, and then you get these three sets, and you discover that those three sets cover all the cases except the prime to prime case. Have I really shown that's generally true? I think I have. I think I do give an argument in here that these sets, when you look at them, they all always have multiples of a prime, and hence that's a composite. And then the other part, this part where it adds, Dirichlet's stuff kind of rivets in here a little bit. Are these always primes, and sometimes they're primes. And this 3m plus 4, this 2m, 3m plus 2, this one is a little odd duck here, the evens. There's a prime 3, this should be a 5 here, a typo. So these are definitely composites. As I say in this thing, that I miss the multiple of 5, which is just 1 times 5, but the rest are composites. So that makes them all composites regardless of this stuff down here. So that's a pretty good argument that this is generally true, that you're going to capture all of the composite 2 primes cases up here. And but then the other part, the cross classification, cross-reference to 2 tables, shows that 4 columns remain. These columns have no numbers divisible by 1 or more of P44. Those are the primes less than the square root of 44, and so give 2 prime numbers as needed. In more technical jargon, we are using the principal cross classification as developed in Apostle. You'd really like some closed form, which, frankly, might be as difficult to do as something like the prime number theorem, the complicated thing with complex analysis and residue calculus and all kinds of stuff like that. But I'm not sure about that. Just to repeat the main theme there, I like the induction one better than called the direct square root of 2n1, where you do a case study with some stuff that does seem to generalize, and the cross classification, the sum of all of these sets, the cardinality of all these sets minus pairing, and then plus, triples, then minus quadruples and all that stuff, which is pretty complicated, yields a number greater that leaves something from the sum, the union of all the singles. And those can only be prime to primes. The part I haven't mentioned in that paper is when you introduce, and I think Melvin kind of liked this idea, maybe Beatty, the inverse of these linear functions. And I've done some study of those, and you do get these striking symmetries. The primes, I conditionally format them in a color, and they exactly marry a prime up there with all the inverse functions generated by this square root stuff. They are perfectly symmetric, and if they're all non-fractional or all fractional, non-integer, non-integral, then it's definitely a prime. But I haven't been able to say that one for sure exists. It seems like the proof you'd like is something like in a domain, all of these linear functions will be forced to all have a fractional image in this domain. And hence, if they have a fractional image, then that is a prime. Ergo, the prime exists. But to prove that, it's kind of beyond my pay grade here. That seems difficult. Seems to get into Dirichlet and all of that stuff. I guess modular functions, Apostles, second edition. I guess Melvin Nathanson has written a book, which I'm tempted to buy if it was only a little cheaper. I had a used one under $20. I think this is in his, Pelosi says her zone for batting, Now I'll get to some new stuff. So I like that induction proof. I like it because it's pure logic, and I think it holds. A counterexample would blow it out of the park, but I don't know how you generate a counterexample. Anyway, let me go to part 2, which is on to the twin prime problem, which I have something to say about.